Hi and welcome back. So now that we've been looking at redox reactions and how we actually generate electricity from a chemical potential energy, looking at those direct transformations, we're now going to look at the application of these to cells and batteries. So batteries are essentially types of galvanic cells. When we talk about cells, we have a half cell, two half cells make one cell, and then multiple cells make what we know as a battery. They are using a spontaneous redox reaction as a source of energy, remembering that when we put the reactants of the spontaneous reaction together, they will react exothermically, just giving off heat. That spontaneous reaction generates electricity when we separate the two half cells and make the electrons transfer through a wire or a means by which it generates electrical work. The chemical potential energy is converted directly into electrical energy, and we do get heat as a byproduct. It's easy to remember this byproduct because you will know from your phone or your laptop or anything like that that when the battery is running for a long time or being recharged, it generates quite a lot of heat. There are two basic cell types that we need to be aware of in VCE chemistry. One is primary cells. These are non-rechargeable. So primary tends to mean first or one, and they have one function, and that is to discharge only. Okay, so primary cells will discharge only. They can't be recharged. Okay, these are non-rechargeable cells, whereas secondary cells are rechargeable. They have a discharge cycle when they are producing power, and they have a recharge cycle, which is where we connect them into an electrical power source and they use power to recharge the actual cell. So primary cells, as we said before, cannot be recharged. The products essentially slowly migrate away from the electrodes and are consumed by side reactions. This means that they're not going to still be available for reaction. Okay, they're not going to be able to react. The cell will steadily go flat, and there's no way that we can reverse that to recharge the cell. So when the reaction in the cell reaches equilibrium, the battery goes flat and we need to buy a replacement. This includes cells such as dry cells, alkaline cells, and button cells. So the ones that we often see used for watch batteries and things like this. Older alkaline and dry cells that we don't see as much, but our AA and AAA batteries are these kinds of cells as well. We're going to look at a couple of examples of cells during this time. It's not necessary to know the individual cells, i.e. you don't need to memorize what a zinc carbon dry cell is. What you do need to be able to do is look at a cell, work out what the anode is and what the cathode is, and that from there the reactions that will be occurring, or answer questions relating to that cell in terms of the oxidation, reduction, electron flow, etc. One of the first ones we're going to look at is a zinc carbon dry cell. This is a single battery or cell. It has a moist zinc chloride and ammonium chloride mixture within it. This is our electrolyte. It's not a pure liquid or solution, okay? It's sort of a moist paste, remembering that these are used in portable devices and things like that. So you can't just have the liquid half cells or the solutions of the half cells in them for transport reasons. So the electrolyte is a mixture of ammonium chloride and zinc electrolyte. And then the zinc casing itself is the anode. So being the anode, this is where we get oxidation. So if the zinc is acting as the reductant, it will be oxidized, and zinc will be oxidized to Zn2 plus 2 electrons. At the cathode, the electrolyte is also mixed in with a paste of carbon and manganese oxide. Okay, so at the cathode, MnO2 and the ammonium with some electrons forms Mn2O3 plus 2 ammonia gas, which stays dissolved within the electrolyte and water. This cell produces around 1.5 volts, and you will notice that this species here doesn't appear on your electrochemical series. So this half cell you would be able to derive from a diagram or given in the exam. What happens is that the products tend to steadily build up around the electrodes. You can see that this is producing a solid here, which slowly stops the reaction, okay, because we get that polarization or a buildup of charge and products around the electrode, it can't react anymore, so it slowly goes flat. With these cells, these are quite old cells, when they were rested, i.e. stopped being used, the products would migrate slowly away and the battery would recover and could be used a little bit more. Okay, so with cells, we need to pay attention to the states of the reactants and the products. This is critical because some of our products are going to be solids. In primary cells, this will mean we can get build-up around the electrodes and it starts to slow the battery performance or reduces the life we will get from the battery. In secondary cells, this is a critical part of the cell that we will talk about. So with alkaline cells, these have been optimized for longevity. These are what our current AA, AAA batteries are. We have the same situation, but now with a bit more technology built in. So zinc is being oxidized to Zn at the metal rod, Zn going to Zn2 plus 2 electrons. But there is hydroxide around. So this zinc solid will actually react with the hydroxide ions, producing zinc hydroxide. Now we said that you didn't have to know how to balance redox equations in alkaline conditions, and that's true for cohes. But if you have a look here, this is just an ionic equation. We have OH minus aqueous on one side and the OH minus solid on the other, so we're just balancing this the same as we would any ionic equation. There's nothing funky going on with that one. Same goes at the outer steel case. We have manganese oxide reacting with water to produce Mn2O3 and 2 hydroxide ions. This one, okay, you would be given the setup of the products of this and just have to balance it. This gives better construction compared with the dry cells, and it gives around 5 times the life that we typically see with the dry cell. Okay, this is important because it made them better used for devices and things like that as we went. So this is the first mass-produced small-scale source of electricity that we see. At the anode, the oxidation of the zinc is going to produce electrons, and if you think about this, if we are oxidizing the case, it's going to get thin over time, and you may have seen old batteries that have busted and the electrolyte has come out the side of them. Sometimes that can be due to a weakening of the case because they've been used for a long time, so those compounds start to weaken the case and the electrolyte comes out. The last of the primary cells that we're going to look at is a button cell. These are typically used in small devices and produce a higher voltage. These are typically silver or zinc cells. They produce around 1.6 volts, or lithium cells, which produce around 3 volts during the discharge. They're relatively expensive due to the small size and manufacturing complications that come along with that, also the costly materials. These will generally work with the lithium or the silver zinc metals in one part of the cell, separated by the other part of the cell by the electrolyte, which allows transfer of ions, and then the cathode container of the nickel or steel, and then we can have manganese for oxide as well. So these are another type. These are higher voltage, and so they're used in things like that. We can use less of the materials for the higher voltage, so we get the smaller cells, so they're better used for small devices. With secondary cells, these are essentially operating on the same processes. They're known as accumulators and they are rechargeable. To recharge a cell, the products of the reaction have to be converted back into the original reactants. So everything that happens in the cell must occur in reverse. On recharge, we use electrical energy from a charger to produce chemical energy. And then discharge, we have chemical potential energy producing electrical energy. For it to be possible to regenerate the reactants, the products formed in the cell must remain in contact with the electrodes in a convertible form. And this is why I was saying before we need to pay attention to the states, because these will usually precipitate out around the electrode at the cathode. Okay, so these types of accumulators that we see include things like car batteries, nickel metal hydride cells, lithium ion cells that we use in our laptops and mobile devices these days. So there's a number of things that we have to understand for the terminology of secondary cells. So as we were saying before, when a cell discharges, the galvanic process occurs. Okay, so this is where the spontaneous reaction is converting chemical potential energy into electrical energy. On recharge, the process is reversed. So this is a non-spontaneous process, which is why we need to put electrical energy in to convert the chemical energy back. This is known as an electrolytic process. It requires electricity and it's breaking things apart. So lysis in biology, you may remember, is to break the cell apart. So with electrolytic, we're using electricity to lyse or to break apart the reactants, products and get them back into the reactants. The power source's negative terminal is connected to the anode of the battery and the positive terminal of the power source is connected to the cathode. So if we have a look here, if this is our battery, when we are recharging, okay, the negative terminal of the battery will be connected to the cathode and the positive terminal of the battery will be connected to the anode. This means that it changes the polarity of those electrodes when they're operating under recharge. What is important for you to do is identify the processes of oxidation and reduction during discharge and then work out what's happening during recharge. What is always true, whether we are recharging or discharging, is that reduction will always occur at the cathode and oxidation will always occur at the anode. The polarity, however, of those electrodes changes when we recharge the cell. So this is an example of a lead acid accumulator, which is what we see in typical car batteries. These are 6 cells joined together. Each one produces about 2 volts, so we get 12 volts in all. They're connected in series. Each cell will have an anode and a cathode separated by a barrier which prevents contact between the electrodes, which stops them from shorting out. And then the positive electrode is the lead grid packed with lead-4 oxide, PbO2, so the lead dioxide, which is our positive electrode here. And the negative electrode is just our straight lead, which is powdered, known as spongy lead, which is packed into a grid at the anode. So we've got lead at the anode, which will go Pb2 plus 2 electrons, and that's going to be our anode. And then we have PbO2, which will undergo another reaction at the cathode. When the cell is connected to the power supply, the polarity of the electrodes changes. So the polarity of the electrodes is dictated by the power supply. The anode is positive, but oxidation will still occur, and the cathode is negative. Reduction will still occur at the cathode. The redox reactions of the galvanic cell are reversed at each electrode. Okay, so what's essentially happening is when we connect it to the power supply is pushing electrons down into the cathode. So now this is where we will have an excess of electrons because the electrons are being pushed down, and then the electrons end up being sucked out of the anode, so we'll have a deficiency of electrons at the anode. So we're still going to have electrons moving in the direction from anode to cathode, but we will have a lack of electrons at the anode, so it will be positive, and an excess of electrons at the cathode, so it now becomes negative. However, those electrons are still going to be used in a reduction process at the cathode. So when we look at the processes going on in the car batteries, at the anode, we said we're going to have lead solid going to lead 2+, and that is in fact what we do see, but it reacts with the sulfate from the sulfuric acid in the electrolyte and becomes lead sulfate solid, which precipitates around the electrode, okay, at the anode. Then at the cathode, we have lead oxide solid is reacting with the sulfate in the sulfuric acid with some hydrogen ions from the acid to produce lead sulfate solid around the anode and water. Overall, we have lead solid reacting with lead oxide and lead sulfate in the presence of acid to produce 2 lead sulfate and 2 H2O. Remembering some of this will be precipitated at the cathode and some of this will be precipitated at the anode. Then when this is recharged, you will notice it is the lead sulfate. We are reversing this reaction. The lead sulfate reacts with water and we get lead solid and PbO2, regenerating sulfate ions into the electrolyte and our acid. But this reaction, this overall process, is what is being reversed. So we have this process being reversed and this process being reversed to give us the overall recharge equation. A couple of other examples of this, okay, we have nickel-based cells and batteries. So these can be a nickel hydride, a nickel metal hydride, or a nickel cadmium battery. At the anode, it is the cadmium or the metal hydride. The nickel is at the cathode, and this is what will be reduced. So we can see here we have nickel OOH solid reacting to produce nickel hydroxide and hydroxide ions. At the anode, oxidation is occurring. We have cadmium solid reacting with hydroxide ions in the cell to produce cadmium hydroxide solid, which will precipitate around the electrodes, or a metal hydride such as nickel, such as like a sodium hydride or potassium hydride or any metal hydride, calcium hydride, reacting with the hydroxide to produce the pure metal and water. Both of these occurring at the anode because they are producing electrodes. For a nickel-based battery, the nickel compound will always be at the cathode. So I'm going to end this up here with just one last comment on battery life, and then we will go through a lot of example questions in class. Essentially, battery life is a descriptor of how well our battery is performing. There is a number of things that can affect this. It can affect the number of recharge cycles, which means that we can only recharge a number of times before it becomes unusable. It can refer to battery capacity, the total amount of charge that decreases over a time and reduces limitations of battery life. So essentially, these are the things that if you check your battery life on your phone, it's looking at. How many recharge and discharge cycles can the battery sustain? And how much charge can the battery hold in the first place? And where is it at? Is it at 80% of that, 60% of that, or otherwise? Battery life can be influenced by a number of factors. This is loss of reactants and products of the cell reaction, anything that causes us to lose reactants or products. Crystallization around the electrodes can increase resistance in the cell, so the charge doesn't flow as well. We don't get as much recharge. And this can be crystals of the electrolytes or metal crystals that can start to grow through the electrolyte towards the other electrodes. Side reactions, so things reacting with air or other things within the cell so that they precipitate away from the electrodes or are reacting in a way that stops them from reacting in the process of the charge and discharge of the battery. Impurities in the electrode and the cell materials, so impurities in the metals or impurities in our electrolyte, and corrosion of the cell. Of course, all of these, the deterioration of the battery life is also dependent on temperature, and I want you to think about that in terms of rate of reaction and what that might mean for our battery life. And maybe think if you've ever tried to use batteries for a long period of time in cold temperature and what might have happened with them. I'm going to leave that here. This is fairly confusing, and as I said, we will have lots of practice, and I'll see you in class.